All right, I guess we can start. Hey, welcome to this week. This week we are going to do the deep dive for the reasoning models, and then a bunch of things before we start going over the project. The content of the next week is released, and next week is going to be focused on image and video generation, which is just the last piece of generally the Gen AI stack. So far we've been focused on using transformers to generate text token by token. But so far we have not talked about how to generate images or videos. So that's going to be the focus of this week, like the upcoming week. And the project is also going to be around that. So the project is also pushed here. So your goal would be to build a multimodal agent, multimodal generation agent. And then, so it's going to be the last piece of the puzzle. So this is regarding that. A few other things before we start. I found this Stanford video for reinforcement learning. It talks about more traditional reinforcement learning. And then right after that, it talks about RLHF. So if you are interested, and RLHF again was the most important and the last piece in the training LLMs. So if you are interested and you want to deep dive and learn more, this is a really good video, and it's like 19 hours ago, so it's quite recent. So that's one thing I wanted to share. The other thing I wanted to share is this playbook, very recently published by Hugging Face, and it basically talks about the pre-training, like lots of details about pre-training, how big models starts with a small ablation. So it's giving you the practical recipe that is happening in most companies to go from building something in a smaller scale and then gradually improving it, and then finally like the infrastructure and production. So this is going to be an interesting read. All right, so I guess with that we can go to the project. So the focus of the project for this week is build a deep research system. And assuming that we've watched the videos, but if not, it's fine. Deep research system is just simply an agent plus a reasoning LLM. Last week, we learned about agents, and we saw that agents are simply an LLM put in a loop and given some access to tools. Deep research is just the same system, agent, LLM in a loop. Now, the difference is that this LLM is fine-tuned to be a reasoning LLM and thinking LLM. So this LLM now thinks instead of LLM just directly producing tokens one by one, and as part of that is going to be the function calls. But instead of doing that immediately, it would instead think first. And as it's thinking, it would come up with better ways of calling some of these tools that are given and using their outputs and so on. So that's what we will be doing today. And that's what most deep research systems are, like the core of deep research systems are. And deep research is something that is provided by most AI labs, like OpenAI has it, Anthropic has it, I think Grok has it, and Gemini has it. So all of these are providing that functionality, and we are going to build a simplified version. So that's the goal. And the roadmap and the steps are similar to what we've seen. It has the same pattern. We'll do the installation. I've already installed my Conda environment. It's deep research. Let me activate it. Conda, activate the deep research. I think I have to activate deep research too. Perfect. And then this is the environment and the dependencies. So I think mostly I need to just check this to make sure that this is the new version. Pip show this 940. Perfect. So I have this, and then I have the project open. Let me also select the kernel. Great. So, okay, so far good. And now the next piece is the Olama. Let's just also set that up and run it. What was the name? Deep Research 2. Deep Research 2. Llama serve. Great. And now going back to the first terminal just to do a quick sanity check, Llama list. Great. So it's working, and then it's already sent a request here and got the response back. So we are good. I'm going to minimize this so the screen is more visible. All right. So in this project, we are going to start with this Llama 3.23 billion. And then later when we switch to, so this is the exploration phase to play with this model and implement some of the techniques that we learned, like inference time scaling techniques. And then after that, when we switch to building the deep research system, we would switch to DeepSeek R1. And then again, as part of this, you can try other models as well. And the library is here. If you go to this library and select thinking models, you would see all possibilities that we can use at thinking. And also these tools model are also, many of these are also thinking models. So, so many of these can also be used for our purpose. But anyway, so let's get back to the project. Now we have the models. Okay, so here we are going to start with inference time scaling techniques. We are going to see some of those techniques in practice. Just a quick review. Inference time scaling techniques are relying on the base LLM. And by base LLM, I mean it's still instruction fine-tuned. So it's a chat model, but it's not a thinking model. It is not going to think. It is going to produce tokens one by one, like the final answer, as soon as you just give the input prompt to it. So in inference time scaling, we are going to start from that base model. And then we are going to apply some techniques. It can be it's mostly prompting techniques and also some search algorithms. And then use those techniques to make this model to think. Like, we are not changing the parameters of the model, the base LLM. Everything is going to be unchanged. We are just going to write a wrapper around it. And then that wrapper is going to push the model's behavior toward that direction, to think. So we'll go one by one and learn what that means. So we'll start with the first one, which was few-shot chain of thought. So chain of thought, we already know what that means. Chain of thought is in the prompt, we show to the model how reasoning look like. And then since it's already in its context, the model would somehow learn from it and generate tokens in a very similar pattern. So that's the idea behind chain of thought in general, chain of thought prompting. Now, few shot means that we include some example as part of as part of its context, as part of its context. Zero shot COT is just we don't provide an example. We just ask the model to think a step by step or reason a step by step. So now let's implement. The first part is let me delete this. All right. The first part is creating this client. OpenAI. Oh, it's the beginning of the month, and it's again suggesting me auto-completion, which is not ideal because I want to type it. It makes the learning better. But anyway, Llama, and then the base URL is this. So this is the client, and let me run it to make sure everything looks good. Okay, it doesn't look good. Okay, it's just a client. Great. Now we have the client. To be honest, I don't know how the fastest way to turn off the auto-completion. But anyway, so we have the client. Now the next thing is write some examples. So just to save time, I've already written some examples. I'm going to copy paste. It's just a string at the end of the day, but it's just showing some examples in a format that we desire. So we call it few shot examples, and at the end of the day, it's just a string. But then within this string, we are showing some questions, which is typical math questions. And intentionally, we are using math questions because that's one domain that reasoning models really shine. When you want to solve math questions, it's really important to have a step-by-step approach. Basically, all the previous steps would help you to get to the next step. So that's why a lot of times reasoning models initially started in math domain. So we have this math question. It is 3 p.m. in London and the rest of it. And then the answer is like this. London is 5 hours ahead. So we subtract 5. The final answer is 10 a.m. Now, this is the first example. And then the fact that we are providing some kind of like reasoning or sequence of steps, we are hoping that the model would learn from it. And then the next question is, again, another question holds whatever like water. And then the answer is net fill equal 5 minus 3 equal 2. 2 times 3 equal 8. The final answer is 68. Now, this is the second example, and just 2 or 3 examples is typically sufficient for like in few shot prompting, in few shot COT prompting. Now we have this. Now, one thing also to note is that both of these examples are ending their response with the final answer is. So the model is very likely just to pick it up and answer the question that we would ask in a very similar format and ending it with the final answer is. So this is a very powerful thing because it gives us more flexibility to control the behavior of the model. All right, so now we have few shot examples. Now let's also ask a question. A rectangle has, let me copy paste what I have. All right, so we have the question, we have the few shot examples, we have the question. Now let's construct our prompt. Now we can say our prompt equal very simple few shot examples plus question. Or we can also make sure that this question, this is the question that, I mean, here we are just defining it. In practice, it's going to come from the user if we are an app developer. So we cannot expect the user to follow this format, like queue followed by the actual question. So if we really want the model to perform and stay consistent, we have to also wrap this question and make sure that it's following the same format. So what I'm going to do here, instead of just writing few shot examples plus questions, I would do this. I would write this and then question, and then next line, A. So, all right, so we have question and we have prompt. Now, the next part is just picking the model. So the model would be Llama 3. It's so sad that that the autocompletion is just writing all this. Response equal client chat completion create. So this is correct. And then model is good. Then the messages, we have roles and content is good. So the rest of it are just hyperparameters. So I would just set the temperature equal something reasonable here. And then that's it. I mean, the rest we can inspect later. Now we can print the content. So let's see now what happens. What we expect is that the model should now answer this question, but it should not produce the final answer. It should have a sequence of reasoning steps. And then ideally, if the model is good enough at picking things up, it should also follow this format at the very end to say, it should say the final answer is. Let me run this. Great. So we have to solve the problem. We need to find the length of the rectangle. So it's following the sequence of steps. And then at the very end, it says, so the length of the rectangle is 15 centimeters. So one thing I want to note that is Llama 3.2 is already a very good model. It's a very powerful model, and it's very likely that it's already trained on examples with a sequence of steps. But the power of few-shot prompting is more, it shines more when you have less powerful model or LLMs that are not trained on few-shot examples. Or basically, they're not trained on these kind of examples in their training data. Llama 3.2 is very likely that it was trained on those kind of data. So even if we don't provide these examples, I feel like the model would still follow those steps. Let's quickly verify this. So I'm just removing the few shot examples. So it's no longer a few shot setup. So let's see if the model would still produce in a somewhat similar format with all those step-by-step reasons. So again, it's exactly producing a similar response with sequence of steps. And again, that's mainly because the model is good enough and it was like the model is powerful and it was already trained on similar data. So that's one thing. And then the other thing, let me put the few shot examples back. And then we also add a system prompt, role system, and here say strictly follow the format of the examples provided. And just to make it more clear, let's do final answer is. So I'm trying to make the format a little bit more specific to see if now with this additionally provided system prompt, even the Llama model would like look at our examples and try to follow it. So now what we expect is that the answer should now end with this kind of format. Let me rerun this one last time. Great. So the model saw the examples and then it also followed the system prompt and now it's producing the exact same way that I want. So this is very powerful because now I have access to a really good model and then now I can control its behavior and format. So that's typically what few-shot chain of thought does. Now, what we are going to do next, this was optional, but what we are going to do next is this time I'm going to implement also this optional. Optionals are generally meaning that it's just a follow-up like example, so we are not implementing them. But in this case, I'm going to implement because it's going to be interesting to see what happens when we switch to GPT-2. And now GPT-2 is just a pre-trained model. It's not instruction fine-tuned, and it's not reinforced learned. So it's just a pre-trained model. It's very good at completing sentences token by token. And that's certainly like GPT-2 certainly is not a thinking or reasoning model. It was not trained on such data. It was trained on big data, and some part of that like large pre-training data might have had like reasoning steps, but it was not by intention, and it's probably not a lot of those kind of examples. So we are going to switch to GPT-2, do the same thing, and see what happens. So I have this code a little bit here. I'm going to just copy paste. You can ignore this part. It's mostly on my side, on my Mac. I want to make sure that the setup is good and I can run these things faster on my accelerator. So now, so the next thing is we can create a pipeline from Hugging Face. So here is the GPT-2 if we want to use it and then use this model, transformers. Basically, this is kind of the command that we need to use this model. So let me now go back here. And now I load this pipeline, or we can call it anything. I'm going to call it pipeline. And then I'm going to add a bunch of things, D-type, just to keep things efficient. Here, I'm just going to, when I'm loading it, I'm asking the types to be in a lower precision. So float 16 instead of float 32. So now we are using less bytes to store each parameter. So it's going to be more efficient. And then finally, the device. So now we have this pipeline. If I print it, let me not print it here. Let me create a new cell because this is going to take a while probably. It's going to download the model. So it's going to, okay, 5 seconds. And then the device is set to MPS, which means that it should be fast enough. And now if I print pipeline, it's just a transformer object, text generation pipeline object. Now it's time to use my few shot examples. So I'm going to copy paste them and use the exact same question. And then prompt. Okay, so far it's good. So here first I'm going to, so the assignment is asking us to GPT-2, the goal is to test whether a few shot alone can elicit a structured reasoning. All right, so now let's do this. Out equal pipeline, then we pass the prompt, max length or max new tokens. We can set it to 128. And then do sample false. For now, we are just going to stick to the greedy decoding. So we are saying do sample is false. So when it's producing the tokens one by one, and each time there is this probability distribution, and it simply picks the highest probability as the next token. So we have do sample false, and then we have use cache equal false. I mean, this is minor, so I'm not going to explain it, but in practice, we can also rely on some caching mechanism and set this to true, so everything would be more efficient. And now we have this, so let's print it. So what do we expect here? We are providing these examples. So basically what the model would see, let me create a new cell, print the prompt. So what the GPT-2 model would see here is simply some questions starting with Q and then some answers. And then at the very end, it's our real question. Here, a rectangle has a perimeter of whatever, and then the question, and then the answer, and then done. So now GPT-2 is just next token prediction. It's just continuing this. But as it's continuing this, we are expecting that the model should somehow answer the latest question, assuming that the model is good enough. So now let's print this. Going to take a while. Again, because we are using just transformers backend and it's not optimized, so it's not super fast. And also my machine is not powerful enough. Okay, but 27 seconds, and then here's the response. This is just printing everything from the start. And then this was my question, and this was my answer. And then it says a rectangle has perimeter 40 seconds and width 40 centimeter and width 5. The final answer is 6.5. So it's definitely incorrect. Now, this is just because GPT-2 is not good. The size it doesn't have too many parameters, and also it's not trained on very large data. And we are also not using greedy search, which makes it even worse. So if we see the rest of it, because we asked the model to produce 128 new tokens. Let's see what is the rest. So here it answers this. And then it says a tank holds 60. So it's just repeating my question. And that's one of the main issues in general when we are doing greedy search. Now let's change this. Let's make this clear greedy out. And then we also update this. And now let's also see if we improve the sampling like top payout. Pipeline. So everything is going to be the same. This is just the functionality that Hugging Face is giving us. We can easily change some of these flags and then it will switch the text decoding algorithm. All we need to do is we need to just set do sample to true. And then we also provide the top P or top K. Let me do top P. Top P is probably a good default to use. And then top P equals 0.95 or 9, whatever. And then temperature 0.8 to introduce some creativity. And then finally use cache bots. Now let's print it. I'm going to comment this. Or if I comment this, I have to also comment this. So let me create a new cell. Great. So now let's run this one more time and see if it makes any difference by just changing the decoding algorithm. But what is interesting is that the model is kind of following is still the format, even though it's GPT-2, even though it's not powerful and it's just a completion model, it is still following the same format with the final answer is, even for my new question here. So that's at least good. So it can pick up from the examples that we share. So we change the example. Let's just run it again. Maybe this time we were not lucky. Okay, so now this time it says a rectangle has the perimeter and then how much water. Okay, it messed up again. It's just because it's GPT-2. So, but what is interesting is that it is trying to follow some like a step-by-step reasoning. So it understands what it's showing that chain of thought prompting can be very powerful, especially when the model is not as strong or powerful. So I think we can wrap up this section for few-shot COT prompting. And then the next part is going to be faster because now we also don't need to show examples. So here, all we need to do is we need to create our client and a question, and then we construct a prompt and just send it to the OpenAI API. Let me delete this client equal this. And then here we have question like, why do we use neural networks to build LLMs? And then after question, we construct a prompt. So we say, so this prompt, we can also include some like kind of system instruction. So we can say you are a knowledgeable like tutor. Answer the question. And then we can put the question here. And then, so far we just provided like a system prompt in the same prompt and then the question. Now, in order to make zero-shot COT happening, we need to add this, let's think a step by step. So there was this whole paper that was showing that just adding a let's think a step by step zero-shot COT prompting. He was just showing that just adding this single phrase of let's think a step by step can improve the quality of your responses a lot. So I think they had an interesting example somewhere. So it's here. They're just comparing different methods like few shot and then few shot chain of thought, showing some like step-by-step reasons, and then zero shot only when they just ask the model to answer. And then here is what they are proposing, zero shot COT. So all they do is very similar to zero shot. They're not showing any examples, any new examples. All they're doing is that they're just adding this let's think a step by step. And then this alone, they're showing that it improves the results a lot. And then they call it zero shot COT. So we are going to do something very similar. So we add this, let's think a step by step. And now we have everything. So we can just select this model and then response, client chat, completion, create model, role. So let's just remove this because we already added the message here. This is not the best way. It's usually good that you separate your system prompt or like high-level instructions or information that you're providing in a system prompt. But for now, we are just putting everything in a prompt. So we have this as the message, and then temperature, let's just set it very, very low. So that's it. Now we can print it. Let's print in the next cell. All right, so it says, oh, that's because there was a problem here. So now the prompt should include my question too. So let me rerun this. All right, and now if we print it, we would get all the like. Let's break down the process step by step. So the fact that it's producing this kind of thing, it might be because we added let's think a step by step. So it just says it's basically trying to break down the task in a more like detailed and produce a more detailed response. All right, so I think we can wrap up the COT zero shot and few shot prompting. Now the next thing is self-consistency. So a brief review of self-consistency. The idea behind self-consistency, so there was this paper that came out from Google. And then the idea of self-consistency is that, okay, we are given a base model, base LLM, it's not a thinking model. How can we spend more compute when we are generating the tokens so that we end up with a better output quality? And what they're suggesting is that we can, in certain domains like math, we can just, oh, I think they don't have a good visual. Okay, this is perhaps the best visual, but I think my visual is nicer. So let's go here. So what self-consistency does, it's very like special case of best of n sampling. Like best of n in general refers to using the model and sample n times from it, like n different generations for a fixed prompt, and then somehow pick the best response. Self-consistency is more is simpler. What they are saying is that, okay, we have this LLM. In order to improve the quality of the output, let's just pass the prompt and then run generation multiple times, like independent from each other. So we generate like 4 outputs, and let's say this prompt is in a certain domain, like math. So it's easily verifiable. So when we look at this, we can just look at the final output and verify if it's correct or not. So we do this, and then we just see what is the consensus. So this can simply do a majority voting and see if, for example, out of these 4, 3 of them are saying that the final answer is 3, and then one of them is saying that the final answer is 1. So they just rely on the final answer is 3 variant and just show that to the user. So this can be considered as thinking to some extent. Basically, when we ask something from ChatGPT and it shows us thinking, we don't know what's going on under the hood. I mean, there are some fixed set of techniques, but in particular, OpenAI, we don't know. But the moment that we are seeing thinking, it basically, what that means is that they're using more compute to generate more tokens and then figuring out which one is better to be pursued further or finally showed to the user. So, and this is one simple example of doing that. Because the user should just wait until all these responses are generated. And then also the algorithm should pick the majority voting answer, and then it would show to the user. So this is self-consistency, and we want to implement it. And we want to implement this majority voting thing. But there is a more generic case of self-consistency, which is in general like best of n sampling. In best of n sampling, we don't have to necessarily do majority voting. We can figure out a way to pick the best response. It doesn't have to be through majority voting. We can use a separate model, like a reward model, to score these responses and then pick the best response. So this was I wanted just to share some context before going to the implementation. So let's go here. Now we want to do self-consistency. And now we have the client, we have also the model. We want to implement some functions. And then once we have these functions, we want to send this question, what is the square root of 144? And then we just run this function, self-consistent question, send the question. And here by default, it runs 10 different generations and then pick the most frequent answer. For the start, I'm going to send 4, but then I'm going to switch to 10. And then here, the output of this self-consistent function that we are going to write is the winner and the counter, how many of those generations were believing that the answer is something. And then we print the counter and winner. So that's what we are going to do in this cell. And then this COT answer is where just where we generate a step-by-step reasoning chain for the given question and extract the final answer. So remember, we need the final answer. We need to extract the final answer because right after that, we want to run majority voting. For majority voting, it's just a simple fixed heuristic. So we need just one single number. Otherwise, the majority voting would fail if it has text because it might be in different, there might be different wordings. So this is what this COT answer would do. We are going to send the question to an LLM and then get the response back. And then we are using some regular expression to extract the final answer from this from the response. And then we would send it to, we would just return it. So let's do it. Let's have a system prompt, or I'll call it prompt. Answer the following question with a step-by-step reasoning and final answer after. So this part is very important because in order to easily parse the final output, we have to make it very unique, like the format of, like the format that the model would show us the final answer in its output. So that's why I'm just introducing something very unique here, like therefore or final answer. I'm going to do therefore. Therefore. So that can be the prompt. And then let me also do this. And then here I'm going to send the question. And then here I'm going to also do, let's think step by step. So I'm basically using all the techniques that we've learned. I am doing zero-shot COT prompting. I'm also asking it to follow a very specific format so I can parse. All right, so it already completed the code for me. I get the response here. Now I'm not going to return this response. What I'm going to do here is, let's just remove these things so we can test everything. For now, let's just return it. And then I write test so it completes for me. What is the square root of 144? Let's just run this for now. It's just a simple, like one generation. All right, it should look good now. Great. So the final answer is correct. And then it's also following a step-by-step reasoning, which is great. Now, if I run this one more time, it may not necessarily show the correct solution. Now, this is a very simple problem. So the model we are using is powerful. So it's likely that it would produce the correct answer. But that's not always the case, especially if it's switched to a less powerful model. But now, so basically let me first increase this, like 1.4, and rerun this. By the way, the previous one was not good enough because after the therefore, it was a comma and then it was empty. So we have to fix this prompt. Okay, here it says, therefore, this isn't the best answer from. So just because we increase the temperature, the answer is not good enough anymore. And I'm intentionally increasing it a little bit because we want to see the value of self-consistency. If it's very low, and since the model is good, it would always produce 12. So self-consistency is not going to be, it's not going to like show the point. So let's just stick to 1.1. And then here, let's just clarify that answer the step by step and final answer after therefore. For example, you produce steps and then say therefore 12. Not 12, like therefore like actual number. It's not gonna work. So the reason this part is important because we want to extract the number from it. Therefore 15. So now let me rerun this one more time to see if it looks good. Maybe this is what confusing the model. Reasoning and only include the final number after therefore. Anyway, let's just continue. This is the best we can have for now. I think if we decrease this, it may work. Oh, that was a good one. Um, anyway, so I don't want to spend more time here. We'll see 10 generations soon anyway for the self-consistency. So let's just move forward. So here I'm going to extract the content from the response. And then here is just a regular expression that I had from before. I'm not going to explain it. I'm just asking it to follow the therefore. And then right after therefore is basically the final output. So just extract that. So here, then we have the match. And then here we simply return the content as well as the match dot group one dot strip. I mean, this is just some formatting and minor, so I'm not gonna go over it. And else none. So now if we run this, let's see what happens. The main point of this exercise is just to understand the implementation and self-consistency. I mean, whether the model make it correct or not, that's not the point. Just the important part is that how self-consistency can be really implemented in practice, and what does it mean that when we say models are thinking. So, all right, so we have the output here. So it says to find the square root of whatever. This is the content. And then I think somewhere it should be the okay. There was no match just because the model is not following the therefore part. So let me just switch to what I originally had. All right, so we have this function for extracting, sending the request to the model and getting the response back. And then let's just reduce this. So this is already tested. Now let's go to the next function, which is self-consistent. So here we are just gonna have a list of answers, and then we'll just go over we'll go like we generate n times using the model, using the COT answer. So this many time generate the answer, and it's the opposite because we want the match. We want the extracted match. We don't want the actual content. So we do this, and then so we have the COT answer of question. Now we should append it, answers.append. And finally, we just need to run the majority voting. So we can rely on the Python's collection counter to count. And then after we have the counts, we can get the winner. winner and this counter most common. So these are minor things. I had to search online and read the documentations to understand how it really works, what it expects, like the 0 and 1 and all those things. So don't worry about those. In general, it's very difficult to remember all this. So it's always best to do like um, collections, counter, Python, and then it would just show like what it expects, how it works, and how you can use it. So, yep. And so we have this winner here, and then we return the winner and the counter. I believe this should work. Now, let's just run it with 4 generations. So now we are basically, we are going to have 4 independent generation, extract their final answer, and then run majority voting, and then show it. So let me run this now. It's going to take a while because now it's going to run it 4 times. It should end anytime soon, like 4 times 9, 36. So we should expect it ends at around 36. Great. So, oh, actually, it worked. There was 3. So 3 of the generations, they were saying 12. And then even this one, which was different, is just because of the formatting problem. Probably if we spend more time on the prompt engineering, make sure we have a good prompt. We also produce some examples and include it as few shot examples in the system prompt. This won't happen. Now, if I increase this to, if I increase the temperature to 1.1, let me rerun this quickly. We would see more variations here because now the model is more creative. It's occasionally would pursue like incorrect directions, and then here we would see more like different numbers. Let's just do it. Okay, 20 more seconds. But that's basically the high-level idea of self-consistency paper. The implementation is very simple. Usually just 2 functions. One is the pure generation, and then the other is just running that function multiple times. Now, if we switch to more generic case, which is just best of n sampling, here instead of doing majority voting, you need to implement your own like a scoring system, which can rely on some other LLMs. Basically, now here at this point, you can send these answers to another lightweight LLM and ask it to score it and get the score back. And then here just return the winner, which is the highest score. All right, so here we get these votes, and then, okay, now the answer, it's not ideal anymore. So that's self-consistency. If you do prompt engineering correctly, if you set this temperature to something reasonable, it would generally work quite well because now you are spending more compute and then letting the model try different approaches and then pick the best one, like pick the most consistent one. So that's one way of introducing thinking to the non-reasoning or non-thinking models. Now remember, this llama model that we are using, it was not a thinking model. It is a reasoning model in a sense that it generates sequence of reasons, but it's not a thinking model. So what that means is that whenever you ask a question from it, it's not going to think. It's going to just produce answer. But with this mechanism, we are just forcing this thinking process. All right, so we are done with self-consistency. The other thing that we would implement is sequential revision. Now, sequential revision is, again, a quick, just to give a quick context here. In sequential revision, things happen in a sequential form. So now instead of asking this LLM to generate independently and in parallel generate multiple responses, we ask the LLM to generate something, and then we ask another LLM or the same LLM to revise it. And this can happen multiple times. In practice, I've seen K equal to 2 or 3, meaning that we have 1 or 2 more follow-up steps to revise. But theoretically, you can just increase this number. And as you increase, there is a trade-off. You are spending more compute, which is not ideal, but you are likely to get better revisions. So, all right. So let's go here. Great. So here the implementation is not it's straightforward. We first create let me delete this. So we first create the messages with roles, and then the system prompt, and then the role. So here we can say you are a helpful assistant. Keep your answers clear and correct. And then we have the role with a user and question. So this is our message. Then next, I'm going to first create a draft. This is the first time for the first generation. I manually send this request to the model and get the response. So this sounds good. And then right here, I'm going to just get the message.content.strip. So here I'm just getting the output. So let me print draft to see if everything is working. Would equal sequential revision. This question. So let me run this once to see if it's working. Oh, all right. So it's working. It's returning the draft. This is the first draft. Now, what we need to do next is we need to now do the iterative process, start the iterative process. It can be as simple as just having a for loop for these many steps, max steps. And then here I'm going to just copy paste and then explain it just to keep it consistent with the solution that we would release. So here is the system role, and then the content is just simply you are a helpful assistant, improve answers by making them clearer and more accurate. So all the subsequent calls are going to have this system prompt, which is we are explicitly asking to make it more clear. And then the user, which is the question, the original question. And then here we are going to send the draft. And this draft would keep getting updated each time we are in this loop. And then finally is the user, which we are asking as the user prompt is please revise your answer, make it clearer, more accurate, and better written. Only include the new answer. So everything looks good. Here is the new role that we've seen. We have typically an assistant role as well. And that's what we and this is how the model would know which responses or which parts are generated by the model itself. So if you go to tick tokenizer and select one model like something like GPT-4. So you would see we have system prompt, user prompt, and assistant. Assistant is used more to like maintain the chat history, because in chat history there are questions from the user and the answers from the model. So in order to separate these things, we have this assistant tag as well. So here within the assistant, we typically put like the model's output. So all right, so that's why we are sending the draft, because it was generated by the model. So we want to make sure that the model knows that this is just the assistant message. So now we have the messages. It's just as simple as now creating the next draft, send everything to it, getting the response, and then that's it. Now in the next iteration, the draft would be sent back again, and then the model would try to just make it better. And then after this for loop, we are done. So we can return draft. Now, if I run this, I expect to see, let me add a print statement here too. Print draft. Great. So now at each step, we are gonna print the draft. So now here, we don't need to even print it anymore. So let me run this with three steps. So the draft one was to find the area of the rectangle. We need to determine its dimensions, and then it's just continuing that. So I'm not going to verify or check the answers. The purpose is just to show the implementation and the idea. So now here, so it's okay. So now it's processing this, and it's probably producing the second draft. So draft one was here. Draft two is here. To solve this problem, we can start by setting an equation. So we see that the output is becoming different from the first attempt. And then draft three, which is the final one, is here. To solve this problem, we can start by setting up the equation and so on. So this is another way that thinking model works. So they just, under the hood, they just continue refining and making the draft better and better. And then once it's done, then they show this final answer to the user. So this is the moment that you would see in chatbot UIs that the model start producing tokens. While it's working on this, you may see things like thinking icon, or some models may be open source and show the thinking process as well. So that's sequential revision. Next is tree of thoughts. And tree of thoughts is a bit more advanced. And what is going to happen in tree of thought is at each step, we would generate, we have some partial solutions or a set of solutions. And then we try to like prune this tree efficiently. So for example, if a partial solution is not ideal or it's not going in the right direction, we would just stop continuing those like branches. And then the good branches, we would just continue doing it. So the important piece that we need for TOT to work is we need to have a function or module that, given the question and a partial answer, it can give us some scoring, that how good this or how likely this partial solution is going to lead to something good. So that's mostly what we need. And one thing to point out here is that tree of thought and self-consistency that we saw is not very different. Basically, TOT is just more efficient, because in chain of thought, we are just blindly having like n different chain of thought generations. And then at the very end, we figure out which one is good. Here is more efficient because yes, we start with n or even more independent generations. But then as we are continuing these generations, like each time we generate a sequence of thoughts or steps, we prune them, prune the like the bad directions. So it's going to be more efficient. So what that means is that it's more efficient. So we can now, for the same compute that we previously spent for self-consistency, if we spend it for TOT, it's very likely we get better results because it allows us to explore more branches. So yeah, that's what we are going to implement for TOT. And for this one, I'm going to copy the code and then we'll just walk over it because it's less AI related and it's more like just pure algorithmic implementations and it's pretty straightforward. So I'm going to just copy paste and we'll go over them. All right, so here we are going to implement tree of thoughts and we are going to implement it for two different examples. One is a word ladder puzzle. Word ladder puzzle is given a vocabulary, a set of vocabulary and source and target. We want to have a sequence of possibilities to go from this source to this target. This is a simple like algorithmic question and there are different implementations in dynamic programming and so on. So they're not AI based or like LLM based. But here we are just want to use this example as a way to understand tree of thought and everything is going to be like LLM based. So it's not deterministic necessarily. It just all depends on what LLMs think at any given step about a partial solution. And if it feels that it's in the right direction, we can just continue that direction. But there are way simpler implementation to solve this problem in like pure data structures and algorithms. For example, in this example, we are given heat as the source and the cog as the target. And then this can be one possible solution like heat, hot, dot, dog, cog. So, all right, so that's the problem we want to solve. And then we want to implement this tree of thought functions. We have a start, we have a goal, and we are given a vocabulary. And we want to just now practice forming this tree. And at each step, we calculate if a partial solution is good enough or not. Again, this word ladder puzzle here, the goal is just to practice implementing tree of thoughts. So this particular example is not also LLM based. It's just a practice to implement forming this tree. And as we are moving forward, we introduce some reward or a scoring mechanism and a score. And then based on this score, we just run this search algorithm and see if we ever get to the output, which is the target. So just to clarify this point, so this is not an LLM based. So this is a start, this is goal. And then vocab max depth is indicating like how deep we are okay to go and form this tree. So we don't want to, because certain branches may go forever and may go too deep. So we don't want that to happen. We want to constrain that. All right, so we have a helper function here, neighbors. Given a word and vocabulary, we want to find all the neighbors, all the other words in this vocabulary that we can transition from this word. So this can be we are just simply enumerating over all the characters of the word. And then we are also going over all possible English characters, assuming that everything is in English and lowercase. And then we say that if the character is not the same, and then if everything else in the word is if we change only one character, like the ith character, and change it to something else, if it exists in the vocabulary, so that word is a candidate word, basically a possible candidate to transition from this word to that word. This is just one implementation. There are different ways that this can be implemented. So it's not important like how we implement it. So this is neighbors. And then the tree of thoughts here, we have, we go over all the depth. And then at each depth, we have the candidates. So now for each partial path, so this frontier is responsible to keep track of all the partial path. Like at any given time, like if we are at a step like depth 2, it would hold these partial thinking like these two. It would hold these two, like all like whatever, and it would not basically would hold anything, any candidate partial solution. So all right, so we just go over them and then we see if um, so basically here we just try to, it's easier to explain here. At each partial solution, first we want to know what are all other possibilities that we can expand this partial solution. So we want to expand this partial solution one step. So this is what's happening here. And we form these candidates. These are all the candidates. Now, the next thing is that, okay, which of these candidates should we explore? So here we need to specify a scoring mechanism. So for the scoring, it can be anything. In practice, when it's LLM based, it can be an LLM scoring. Here, it's just we use some heuristics as the edit distance to the goal. So how close we are at this partial solution to reach to our target word or goal. So we just sort all these candidates. And then based on this provided beam width, which is 4, we expand our set of partial solutions and keep the top 4. So again, here, let's say from here, there are 10 possible expansions. We sort all of those based on how close they are to get to the output, like their distance. And then we pick the top 4, and then we add 4 new partial solutions to our frontier. So that's basically it. I mean, I'm not gonna spend more time on this. It's very like algorithmic. But if you can review this, it's already released on the Git repo. So you can review it, but this is working. We are just building a search algorithm and then forming this tree and using some heuristics. Here is negative edit distance. We form it, and as soon as we meet the goal here, we just end it. So here you see that the output is a sequence of a correct output. Like if we go from hit to cog, and then each step is just one word, one character different. So now this was just to warm up to understand like tree of thoughts, how to form a tree and how to keep track of partial solutions. Now here we want to build a more generic TOT search. And now this time it's going to be AI based. So now we have this question, design a plan for a weekend science workshop for the 12 years old. It's all messed up. So anyway. So what we want to do is we want to run this tree of search, and tree of search would just go for depth of 2 and width of 2, build this tree, score partial solutions, and as soon as it reaches something that is good, it would return the solution and the score, and then we would just print it. So now we want to implement this. So still, I'm going to copy paste because there is no point to write this. This is going to be very similar to what we've seen in earlier section. So here for the proposed thought, here is where we are expanding. So it's equivalent of like where we are like, this here we are expanding. And then this part in proposed thoughts, our goal is to given a question and a state. And we want to like propose up to k next thoughts to extend these partial solutions. And then this is specified here. You are exploring solutions. This is the problem. The current partial solution is this. Propose at most k different next thoughts. And then we just leave it to the LLM to figure out what each what a thought means. But most of the time they do reasonably good. So now, and this is just a typical sending request, and then we get the response back, we return it. So here we are just expanding. Now, here we need to score a given state. So here again, it's just all like coming up with a good prompt and sending it to the LLM. Now, these LLMs, we are using the same model. In practice, it can be different. For example, for scoring, it can be a model that is specialized or very good at scoring, or it can be a reward model. Or you can use at least a very lightweight model because it's a simpler problem than generation. It's just you're giving a question and a state, it just needs to score it. So this all of these are context dependent. So depending on what problem you are solving, like you figure out what is the best model to use. Here we are just using the same model. So here we send a problem and then we ask it to rate from 0 to 10 how promising this partial solution is. So we have our two helper functions, one to score a given state, one to expand it. Now we can implement our tree of thoughts. And the implementation of tree of thoughts is similar to what we've seen here. So let me print it. So again, we have a frontier. In the very beginning, it's an empty. So the goal is to go over these and expand this and then score them. And then as we are scoring them, we can also introduce some filtering mechanism, but we don't have to. So it all depends on, there is a lot of flexibility. So we start from something for the number of depth. We have like these candidates. Then we go over all the current partial solutions. We propose thought. And then now with that thought, we form a new state. We score it. We add it to our candidates. We sort all the candidates. We keep the top K like the top K responses that are more likely to be good. And then everything there, we just add then the width, like two more partial solutions to the frontier. So these are for us to just control, like when we are forming this tree. And then at the very end, we have this frontier, and then we can just print it, or we can get the one with the highest score. So we have in the frontier, we have the partial solutions and the corresponding score. So that's it. We are returning it, and then let's just run this and ask design a plan and see how it works. I'm trying to remember how long it used to take to. Oh, actually, so while it's running, the next section is training models. So we are not going to go over training. It typically requires compute and infrastructure. There are some explanations here if you're interested. The pseudocode is always very simple. When we want to train a model to be a reasoning or thinking model. So far, we've explored inference time techniques. In the lecture, we also covered training time techniques. And training time techniques is when we start from a base model, we update its parameters so that it becomes a thinking model. And one very good example of thinking model, it's also shared in the lecture, is DeepSeek R1. And then in DeepSeek R1, it's already trained to think. So what that means is that when you ask a question and it starts to produce tokens, first the tokens are within a thinking tag. And then after that, it generates the final answer. So, and there are different techniques to train a model to be able to reason and later think. One example was a star, and a star is just to train on chain of thought reasoning inputs. So we collect data in a format that it has a sequence of reasons, and then we continue SFT the model on that data. You can read the paper. It's called Self-Reasoner. The pseudocode is very simple. We keep collecting data and the data is in the form of like step-by-step reasons or rationals. And then we fine-tune the model on that data. And then we again use this new model to generate better rationals. And then so there is this loop. So the model just keeps getting better and better at thinking. And then here is just the reinforcement learning methods. And then reinforcement learning methods is just we generate some reasoning, and then we based on the reasoning, we score them, and then we apply the PPO to update the parameters. So the model becomes better at generating outputs that are more valid or more like the reasonings that are better. All right, so getting back here, we have the answer. It took 1 minute, 30 seconds. Again, my machine is not powerful. If you run this on Colab and with some GPU or TPUs, it's going to be much, much faster. So here it's just showing me the best solution with a score of 8. So what that means is that the model already explored different solutions, and then it came up with different scoring for different solutions. And then eventually the best solution and the score was 8. So this is another way of introducing thinking in non-thinking LLMs. So great. And we have also completed here. And then training is, we also covered that. So now the next part is the deep research agent. Now, here is where we are going to, so this part, the section 4, is similar to the last week's project. Now, the main difference is that we are going to switch to a reasoning model. In this case, DeepSeek R1. Because again, in deep research setup, the goal is that we go and search different websites, collect their information, and then come up with a final output. So it's kind of a research task. And in order to do the research task well, usually we need a thinking model, a model that can think first. And as it's thinking, it may come up with a better way of like what search queries to use, which websites to search, which information to collect, and so on. So that's why deep research is traditionally was using a reasoning model. So again, the code is very simple, so I'm not going to implement this. Let me just copy paste the code here. It is exactly the same code as the last week. So here we just send the query and get the actual body of the response as the result and send it. This is our search tool. So last project, we saw that we can do this. There is also another way we can create tools, and that's by importing tool from langchain.tools and explicitly creating a tool object. So here we say that the name is this, the function is this, and this is the description. So now from this, LangChain would be able to generate a schema for this tool. It's just a different way of generating this tool. So let me run this. And then here. So here now we are having this model. First, we would initialize it, then we build the agent, and then finally we ask a query. So I'm going to just copy paste here. Same as before, we are using Ollama. We create this LLM with this model, DeepSeek R1 8 billion. It may crash on my laptop now. I may have to restart, but if it happens, I would do it. So this is temperature. The agent, similar to last week, we initialize an agent, and then we pass the tools that we already specified here, search tool, the LLM and the agent type, and then we keep the verbose to true so that we can think this loop process. And then our question is, what are the best resources to learn machine learning in 25? And then we can just invoke it. So let me run this. While it's running, you would see so while it's running, I have something to share. So last time we saw the zero shot from description and those kind of agent types. This time we are using OpenAI functions. It's basically a different way of, you can think of it a different kind of framework. So instead of following a React framework in that particular style and enforce it through prompting, here we are using OpenAI functions. And OpenAI functions, so all like what is happening under the hood is that we are using a model that was trained for tool calling as well. So this model was trained for tool calling. So it already knows, given a set of tools, it's trained for that. So it already knows, okay, whenever I'm given a set of tools, these are the tools that I have to pick, and this is the format that I have to request for the tools to be called. So this model is, and in most cases, the models that were trained for tool calling, they produce their output for tool calling in a certain format, like in a JSON format. So it's no longer a React format where we specify the model, like in the prompt, we tell the model, hey, follow this format when you want to call a tool. It already knows, and it already follows a certain format, which is typically a JSON. So OpenAI functions just simplify this process. It no longer relies on a React process. It expects a model trained for tool calling, a set of tools so that it can extract the schema. And then when it passes those tools and the question to the LLM, and then the LLM wants to call some tools, it would produce the in a JSON format. So LangChain already implemented this. So when we say agent type OpenAI functions, it's still the same loop. Now the difference is that the parsing is different, because now the expectation is that this LLM would output its intention to call tools in a different format. And OpenAI functions is just agent type OpenAI functions, while LangChain already knows how to correctly parse it. So that's the main difference. And the main purpose was to also show different variations of these things. So that was one different. So now it's still running. It's been 2 minutes and 25 seconds. So while it's running, I'm starting to hear some noise from my laptop. Okay, I'll give it a little bit more time to run, but it should work. So in the meantime, this is optional, so we are not going to implement it. It's just an interesting assignment or exercise if you are interested. In practice, deep research feature is multi-agent. It's not a single agent. Here, we created a single agent. In practice, multiple agents, each of them individually go and search the web, collect the information. And then there is a coordinator where is also an agent, but it's just responsible, like it's a lead research. Sometimes they call it lead research. It's just responsible to collect all the findings from all these sub-agents and then clean them up and return it. So that's how, in practice, this is implemented. So if you're interested, you can just implement it, multiple agents, multiple sub-agents, and one lead agent. So that's it. Let's just give a little bit more time to see if it works or not. All right, okay, it ended. And then this is the process. So you can see the thinking tags. And that's what I meant by thinking models. So DeepSeek R1 was trained to think. What that means is that anytime there is some input, it's a next token predictor, but it always starts with think. And then here is the thinking process. So here it says, okay, user is asking about best resources. First, I need to consider what makes a resource best, and then it adds more clarification and then comes up with a systematic way. And then at some point, it determines that, okay, I need to call the web, and then produces the tool calling request in JSON format. And then LangChain takes care of the rest. It just sends the request, get the response back, send it back to the DeepSeek R1, and then DeepSeek R1 continue generating. And then finally, let's see. And then finally, at this point, it is done with the search, with the thinking part. And then, and basically at this point, it's done, like the entire agentic process. And then here is the final output. This is the thinking part. And here thinking ends. And then here is the final answer, which says, okay, let's break down the best ways to learn Here are the best resources, foundational knowledge, and some more details, and core machine learning, and even some websites. What is interesting is that many of these are obtained online from internet by searching web. So yeah, that's a simplified version of DeepSeek. And we also saw different ways to make a model think at inference time and also at training time. So with that, I think we can now switch to questions. So there was one thing, I already shared these two resources. I there was a lot of requests about some resources on like some links learning more about AI security and some other stuff. So I created some PDFs with some links that are, I manually went through those and they look very useful. So I'm going to release them soon. So in case you are interested to learn about a certain topic like LLM security or context engineering or things like that, you can follow this text. I would release them soon. So that's it. I had a bunch of other links open. I wanted to go over them, I think. Oh, actually, no. This is the function calling. If you are interested to learn more about the function calling part that I mentioned, like models that are trained to call functions in a JSON format, you can take a look at this page, OpenAI function calling guide. So yeah, that's all I wanted to share. So let's take questions now. Rahul?
Hey, Ali. Thanks for the lecture. So one thing is, in terms of training the model, can you share some more details on what's the process if we were to train a model? Do we have
Mhm.
to load a model on a machine, run it in a training mode, and feed the data, whether it's through RLHF or through COT data? What is that process look like if you were to train a model?
Exactly. So if it's pre-training, meaning that you still don't have any model, you create a neural network model, so which we went through in the first week. You create something, and typically it's a decoder only transformer based. And already Hugging Face and many other platforms already allows you to just import it, like just import a decoder only transformer and just you provide the hyperparameters. But anyway, you upload you create your model, and all the weights in the beginning are random. You have also some data. You create a data loader. So data is just pieces of text. You pass them to the tokenizer, you get sequence of tokens, and then you train your model in a loop. You keep passing a fixed length of tokens to the model, and then you ask the model, basically the model produce the next token. And then based on how accurate the probabilities for the next token are, you penalize or you update the parameters. Not you, but the optimizer. So and this is just in a loop. So the optimizer keeps updating the parameters of the model until at some point the probabilities that the model generate for the next token is good enough given your training data.
You would, so I think, I think most likely if a company were to train a model with a specific data set, they would start with the pre-trained model already, whether it's,
Mhm.
and I think that model has to be open source, right? Otherwise, this pre-training will not work, right?
Yeah. Yeah.
So you'll start with the open source pre-trained model, and then you will, I think, instead of starting from the scratch, you would then, based on how that model or what that model outputs, you will look at the data and either feed with the specific data set that you want to adjust the weights for, so that it gets trained on that specific data set as a part of star.
Mhm.
Or the second one you mentioned about the reward model, right? So like, we'll reward the model. So can you share, like, what could be the like steps that we need to follow?
Sure. If that's okay, I can share resources because it's if you're interested, there are a lot of good resources. You can go over them. I can briefly share an overview of how it works. For example, this like NanoChat, I think by Andre. So I think he also, I think he was supposed, I think the training code should be somewhere.
Yeah, you can share it. I think that's
Yeah.
completely fine. You can share it. And
Yeah. I'm
the
going to share this. It's going to be very helpful, and also it's implemented in a fantastic way. It's very clean and minimal. So here's the training loop, like typically. And again, this training loop is the same for pre-training and SFT stage. Just the data would be different. So it's almost always the same. So you go for a certain number of iterations, right? And then here you yeah, perhaps we can take a look at this upline, but this is the fixed training loop that is typically out there for pre-training and SFT. Now, I believe that you would also find the mid-train for mid-trained a model, like same as pre-training, but simpler. And then you may see more code here. So that is a really good place to take a look. It also has tokenizer and like chat web and SFT. So here is the RL part. Uh, so, and it's relying on gRPO, which is a simpler way, and it converges faster, like a different RL algorithm that was proposed by DeepSeek. So here you can see the code as well. So that is one good place to go over, and the other is just the training playbook that I shared in the beginning. It was shared very recently. It was yesterday, like 2 days ago, and it's very lengthy. So I think it would take a while, like many hours to read. I think so. Reading time, two to
yeah.
2 to 4 days. So this would give you probably all you need for training.
Okay, and I'm just forgetting the concept where you have a like predefined model and then you add your own model to it, right? And then the combination of you feed the data in both of these models, and I think the output is dependent upon the output generated by the pre-trained model plus the adjacent model that you develop. And I don't remember what it is called, but if you can share something like how do we start, if you were to start it again, I don't know when or why, but if you were to start it, how would you build that model? If you can share something
Sure.
like some starting point, I think that would be really good.
Yep. Yeah, sure. And this might I may end up emphasizing this even more. I haven't read it fully yet. I just read um, some part of it and it was amazing. So I'm going to continue reading this. And if certain parts are more relevant, also I would share. But sure, I'll definitely
Okay,
share. Yeah.
thank you.
Yeah. Naharika?
Hey, yeah. Hi, Ali.
Hey.
Thank you for today's session. I have a question, like two questions. So one is on self-consistency example that we implemented today.
Mm-hmm.
So self-consistency is all about we are parallelizing multiple generations, right?
Mm-hmm. Mm-hmm.
Whereas in this example, we have a for loop here, right? And that looks like a sequential to me. How are we making this, like how the model is parallelizing this, right? Because I see that this is
Mm-hmm.
in a loop,
Mm-hmm.
sequential
Mm-hmm.
loop.
Okay.
Um,
That's a great point. Um, This is not an ideal implementation. It is, in practice, you can have multiple threads, or you can, in fact, parallelize on multiple machines or GPU nodes. So what parallel means in parallel sampling is not the parallel that you are referring to. So what you are referring to is how to parallelize the compute so that we end up getting the output or the computations faster. In this case, you are right. My code is not parallelized. It can be parallelized easily. In practice, you can just send these COT answers to one GPU and then very quickly gather the responses. So that is different from the what we refer to as parallel sampling. So what we mean by parallel just means that these are independent samples. These are not sequential samples. So no matter how you implement it, you can even implement it in the worst, like least efficient way using a for loop. But the fact that these samples, like these generations are sampled in parallel, so that's why we are referring to that as parallel sampling. Does that make sense?
Yeah, got it. So do you have any references to see how we can parallelize this?
Oh, in terms of the code?
Yeah.
Sure. I can share. Please, just write me a message in one of the channels, and then I can share with you. It's more like,
Okay.
if it's on GPUs, it's like, yeah, I can share.
Okay, got it. And another question I have is on tree of thought. So the analogy you used was with the word ladder, right? So word ladder, we are giving vocabulary, and based on that vocabulary, at every level, it is deciding, right, which one to pick and which one to leave. Uh, so for in terms of LLM, right? How it is getting that vocabulary? Because I see that there is no vocabulary that we are providing, right?
Oh, yeah. So, so in the word ladder, so it's just a different problem setup, right? So for example, for word ladder, if the problem is word ladder, we always have a vocabulary. And then at any step, we can always provide also that vocabulary as part of the context to the LLM if we want to go the LLM route. And then at any partial solutions, like this one and like these two, let's say, we would just pass these two along with the input and the vocabulary to the LLM and just ask the LLM, hey, how likely is it to lead to a good solution? Just score it. Does that answer your question? So the
Okay, so do you
reason
mean
that
that
the reason that in the second part of the sequential revision we didn't have a vocabulary is because just the problem statement was different. It was no longer a word ladder problem. It was more generic. It was just a partial sequence of thoughts. It is not clear to anyone who is the right, what is the right path. It was just a brainstorming, not a brainstorming, but it was a very generic question. So when the question is generic and then when problem statement is not like a very fixed, like a word ladder, it doesn't have a fixed solution, then, and there is no vocabulary, of course. So we just rely more on the LLM to make its own judgment when it's scoring.
okay, so what would be the practical implementation, like in, real world scenario, what are the use cases that we will be solving with tree of thought?
Oh, so it's still parallel sampling. It's a technique like it's the inference time scaling technique to have a model think more, and therefore you discover better solutions before showing it to the user. So TOT is similar to self-consistency. It's just more efficient. In self-consistency, you are this. You independently and in parallel sample these generations. And then at the very end, you figure out which one is the best. And if this is the best, you only show this to the user. Tree of thought, it's still the same. So every time you have a model and you want to spend more inference time compute to show better outputs to the user, you can use it. Just its benefit is that it's more efficient than self-consistency because now you are quickly pruning branches that are not good enough.
But how many branches to span? Like how do we decide that here? Like
This is very context dependent. It depends on your problem, your like memory compute, your the like how heavy you want your search system to be. In general, this is exponential as you are forming this tree, because if at each step you expand each node with 10 different thoughts or partial thoughts, basically at each depth it's just 10x. It's just getting 10x. Like it's exponentially it's growing, right? It's not
right.
10x. It's getting like 10 and then 10 times 10 and then so on. So there is not a simple like number or hyperparameters. You have to experiment with different things and see what works best. I haven't seen in practice depth of like very long depth, like 15 or things like that. I've never seen those. I usually seen like a smaller numbers, like 5, 10. And also in terms of the expansion, I also haven't seen like crazy numbers, like 100 new new thoughts. But it all depends also on the problem and how much additional compute you want to introduce for this, because think of it as a very costly process. Each time you are expanding, you're sending a
Right.
request to your LLM, and the LLMs are costly. So there are lots of trade-offs.
And what is that parameter that we should be using to control this depth? Yeah.
So yeah, one is the depth, like, to what extent,
Yeah.
like how deep you want to form this tree. We had a depth here. I've released the solution, so you can also look offline, but
Okay.
it's
Okay.
basically the depth, which is this for loop. And then the width is like
Okay.
how many new thoughts per node you want to expand, or you want to expand. So these are the main two parameters that you can control the space of, like, your search space.
Okay. So that is controlled by us, like not by LLM, right? This depth
Yes,
and
that
width.
is controlled by you, because this is just only related to your search system. It has nothing to do with the LLM. The LLM part is only here and here. So it proposes a
Okay.
thought, it scores them. It has no idea about what's going outside of LLM, which is a search mechanism. So the LLM has no idea about this search mechanism. It's just like we have this as a wrapper on top of the LLMs. The LLM, just you ask it what to do, it does for you.
Oh, okay. Got it. Got it. Okay. Thank you, Ali.
Yeah.
Thanks.
Sonia?
Yes, hi, Ali.
Hey.
Thank you for the session. So I would like to know, initially when in the terminal, when you activated this deep research environment, why did you choose deep research 2? You had one and then you chose 2, and even in the environment file, it was written, the name is, deep research. Something internal on your machine or something?
Yeah, so it's just my Conda environments. First, I had deep research, which was outdated, and then I created a new one. I just named it deep research 2, but it's the same thing. It's this one.
Oh, okay. I
Yeah.
see something.
On your side, you don't need to do this. You
Oh,
can just do deep research.
okay. And then in the terminal window, you were running this Olama serve, Llama 3, 2 billion, whatever, something like that. And in that terminal, I noticed that you also activated this environment. So is it that, we need
In Olama, I activated it.
Yeah, first when in the terminal window, like there is another tab. There is another. You opened another tab in which you did Olama serve.
Oh yeah. I did because Olama had to be also installed. I think if I
But do we need to activate also in every window?
No, you don't. Even my base Olama runs. I mean, typically you want to activate an environment if you're relying on some pip packages that is not installed in your base one, like base Conda environment. But you don't have to. I mean, right now I was able to just do Olama serve my base Conda. But in general, you want to switch to Conda environments if you plan to use certain pip packages which are installed in that Conda environment. I mean, in this case, it was not necessary. You're right.
And sorry, I didn't get what do you mean by this base? Could you tell what is that?
By what do I mean by
Base?
what?
You were saying something like base. What is that?
Oh, this is just a base Conda environment. So these are just different Conda environments. Like if I do Canva and list, like I have base,
Oh, yeah.
which is the default, and then a bunch of other things. So my point is, if you want to use a library and it's only installed in certain environment, you have to activate it. If
Right.
not, then you don't have to.
Oh, got it. Okay. And towards the end in that multi-agent exercise, I want to make sure if I got it right. you said that in this multi-agent, there are, like, here we are using, say, supposing there is only, in the question is only using web agent, like here. So even this multi-agent, it will have multiple web agents running. Is that what you said?
Yes. Yes.
Oh.
So it would have like, it would simultaneously. So imagine you generate, so here we create one agent. So imagine you have a for loop and first generate a list of agents. And then each agent would simultaneously, you can just invoke them. So they would go search the web, use the tools, collect data that they need, and then would just come back with their own results. Now you also need a lead agent to coordinate. So the lead agent would collect all the results provided by the agent, and then lead agent is also an agent. It's not too different. You can just use a different LLM, but it's still an LLM with a particular system prompt. So yeah.
Yeah. And so like in this multi-agent thing, yeah, I know you covered last time, but I'm asking again. It could be multiple web agents, and also it could be multiple different kinds of agents, right?
Yes, you have full
right?
flexibility. I mean, in practice, it's usually the same from what I've read on like Anthropic and other labs. They typically just create sub agents, and each sub agent is the same, like exactly the same sub agents, but just like 10 different sub agents. And then each sub agent would just go and search the web.
It's just to make things faster, right? Right.
Not only faster, but also to increase the coverage, because with agents, there is a loop. So when they have a certain thinking and then they do function call, they search the web, they may continue going in that particular direction. And they may no longer be able to recover and step back as humans do. So the other benefit of having multiple agents is that there would be more like diverse exploration.
Yeah, like multiple directions those
Yeah,
agents are going.
exactly.
Got it. Okay, yeah. I don't know why I wrote somewhere cleanup question, not add here. I don't know. I wrote where it came from, but anyway, that's all. Thank you.
Okay, awesome.
Yes,
Yeah,
bye.
thanks. Shashank?
Thanks, Ali, for the wonderful session. I have a couple of questions. First is like, we went through these various options of inducing basically thinking in the LLMs. Is there any guideline on like, which method to use when, or is it like mainly experimental driven?
For this one?
Like we talked about self-consistency, COT, TOT, all those various
Self-consistency.
options, right?
Yeah.
Is there any guideline like, this particular method works in scenarios kind of?
Yeah. There are some studies. Again, this whole field is evolving so fast. So tomorrow there might be a new study that is slightly different, or they may come with more findings. But there was a study from DeepMind, and then they were suggesting that for tasks which are simpler, sequential revision usually works better. And that's because if the task is simpler, it's very likely that the model would be just get it right, at least the right direction in the first attempt. So all you need to do is just ask the model to keep revising it, revising its previous draft. Whereas in more difficult questions, let's say like very, very difficult coding questions or math questions, sequential revision is not as good as like parallel sampling. And that's because if the problem is very difficult, it's very likely, it's more important for the model to get the opportunity to explore different ideas in parallel. If you do sequential revision, then as soon as you generate the first draft, the model has no way to recover from it. So it has to just continue revising that. So it's not ideal when the problem at hand requires creativity. To be honest, I don't know what to search for the paper.
Okay, just in case, like, if you happen to find it, it would be great if you can share.
Yeah,
maybe
that's
later.
Sure, I would share it. I mean, I can find it later and share it. That's a wonderful paper. Oh, actually, I think I know a quick way to find it. Yeah, this is the paper. Scaling LLM test time compute optimally can be more effective. It talks about different variants of inference time scaling, and you would understand it easily. I mean, we covered most of this. This is just more theoretical.
Got it. Thank you.
But one section that they have, sorry to interrupt. One section that they have is about the comparison between sequential revision and parallel sampling, and they are sharing their findings, and they are saying that in certain problems they find that parallel sampling works better, especially when the problem is more difficult. Yeah, so just you can take a look. Yeah, sorry, I think I interrupted you. Go ahead.
No, this is great. Thank you. I have one more question. Like we looked at these agents from a specific task point of view, right? But when you're developing a strategy or defining a strategy for enterprise, like agentic AI strategy for enterprise, like are there any case studies done? Like, is there any paper that kind of like tells like what to look out for, what are the best practices out there? I know it's evolving, but I'm just curious, like
Sure.
if you have
I can look and see if I find good papers. I have collected some links I would share soon on different topics. You may find some of those relevant to what you're looking for, but I'll also try if I come up with. The problem is for many of these there is no like single recipe or single strategy. It's really like context dependent, and it depends on a lot of things. I'm going to release this, and also if I find something about like the best strategy or things like that for enterprise, I can also share that.
Yeah, that would be awesome.
Sure.
Thank you.
Yeah, thanks. Viba?
Yeah, okay. I have twofold questions. So one, you were talking about the scoring somewhere, right? So how does that scoring works, and how do we score?
So we don't score. The LLM scores for us. So you pass this input and partial solution, and you provide some very specific system prompt to the LLM and say, hey, score this based on something. So we had this here, I think, for scoring. So for this, so if you see here, this was our system prompt, like a score state. So we asked the LLM to rate from 1 to 10 how promising this partial solution is. We pass the problem and the state, and then the model would just output something.
So it's gonna score it based on its training.
So the LLM basically gonna score it based on its own judgment. So that's one simple way. In practice, like AI labs like OpenAI, they have their own reward models. And then they use that reward model. So that model is specialized and trained for this purpose to score solutions or partial solutions. So they use those models to score. In our examples, we just use the simple LLM, which would work for simple problems like this, like the problem that we saw. But as the problems become more difficult, like Olympiad question, like math Olympiad question or things like that, it becomes more important to make sure that you have a specialized model that can score partial solutions.
Right. So for the question, those are open-ended, and we don't have definite deterministic answers for that. The scoring for that will, that will also be undeterministic. Is
So
that correct thinking?
Can you repeat again?
So the questions, right? Other than mathematical questions that can have a range of correct answers that can be scored, but open-ended questions like philosophy or history or expanding on something. The scoring, how does the model know that how to score that?
I mean, the model is expected to have very good knowledge of the world, and based on the internet, since it was trained on internet data, most LLMs, right? So they are expected to know which answer is better in general. So, for example, here in ChatGPT, if we ask like which answer is better, and then we provide two solutions, like two very, like even out of domain, like very specific examples, the model would still know probably which one is better solution or better output. And that's because these models have seen a lot of different examples. So they've learned in general what to look for, and when they're comparing different solutions. If it's in like creative writing or things like that, they know like these patterns are typically better in creative writing. So they go and look for those patterns in your provided examples. And yeah, they can reliably produce the scores in most cases.
Got it. And the other question is, you mentioned somewhere like if the agent or that particular path of the solution could not recover. Can you elaborate on that? Does that usually happens, and is it expected to happen? And how do
So
we
you
fallback?
mean like a sequential revision setup?
Mm-hmm.
So it can happen, yes. I mean, imagine you ask a very difficult IMO, like math Olympiad question from an LLM. So the prompt goes here. The LLM generates some response as an attempt to solve it. And then you keep passing this for revisions. Now, the problem is that this LLM in the second, like here, it has no way to recover from the original attempt. So it just tries to make it better and better. But in reality, that solution, that initial solution may not lead to the correct final solution. But so in sequential revision, this model has no way to recover from the like initial attempt of this LLM. Whereas if it was like a parallel sampling, these samples are independent. So they don't, if the first one has an incorrect idea or attempt, it's not going to influence other attempts. So that's what I meant by sequential revision. If the first attempt is not in the right direction for difficult questions, then there would be not an easy way to recover from it.
Got it. So it's the way we are passing, like sequentially arranging it. That's the side effect of it, that it cannot recover because it's gonna break the chain itself.
Yeah, exactly. And again, that deep learning paper, that deep mind paper that I shared, so they go in more detail and they share that what are their findings and when sequential revision can be better than parallel sampling.
Understood. Thank you, Ali.
Yeah. Vish?
Hey Ali, good afternoon. Thanks for your session. My question is is a generic one related to Olama setup. Uh, I have an old Mac 2018 model, and the response from Olama has been super slow. It takes like about 2 minutes at times. I tried using Google Colab for one of the project exercise and running Olama in background thread. However, I found that one as slow as well. Is there any like a general guide on what's the optimal way to host Olama, like hosting on a cloud or something like that? I see some alternative suggestions in Zoom chat to like store Olama model on an external drive. Like, does it help getting the response quicker? I was just trying to see what's the like a quicker way to get the response from Olama.
I can check and get back to you. So just to make sure I understand the scenario. So you on your machine, it was a slow, and then your
Yes.
machine is it CPU only, right?
Yes.
Okay. It was a slow, which is expected because it's CPU. Now CPU, and then now you tried on Colab, but on Colab you tried Olama.
Yes, and Colab, what I did was like I got some suggestion from Gemini, and then it suggested that I should run Olama in a background thread so that it can serve the the server is on the background thread, it can serve using that API call.
Yeah.
But even that is slower because like it takes time. Like I see it takes for you like 10-15 seconds or something like that to respond back, and for me it takes minutes, and gets stuck sometimes. So that's where I wanted to see what's the best way to make it quicker, or like if not my machine, how can I still experiment with the concepts that you're teaching, but in a better way.
Yeah, I can please also ping me. I can try. So I'll first try to reproduce on Google Colab and see if I see the same latency, because I have to also see the same latency as you are seeing on Colab. And if that's the case, I'll try to figure that out. I also assume that you picked your runtime on Google Colab, right? You picked the GPU or TPU runtime.
I picked GPU. Yeah.
Okay, I mean GPU or TPU, yeah. They both should be fast enough. Okay, I'll try to reproduce first, and if I were to reproduce, then I'll try to figure out how can it be made faster. I haven't tried running Ollama on Colab just because of those, running the server and all those things, but I'll do it.
Thank you, Ali.
Yeah. Yuan?
Hi, Ali.
Hey.
So I have a question. I want to circle back to tree of thought. Can you explain again what is the max depth and being width relate to? Is it how we define the tree? So the max depth is to how deep the tree is, and then being width is how many number of the child nodes we define the tree searching space.
Yes, exactly. Those are the hyperparameters when we are which basically specifies the search algorithm. Like the depth is like for how deep we go and expand the partial thoughts, and then the beam width is like how many new childs we add at each partial solution.
Got it. And then the frontier is just we record the top K possible path.
Yes.
In the searching space.
Yeah. Basically, in frontier is you are just keeping all the partial solutions that you still have hope for. you drop the ones that you no longer have a hope for. So frontier is just every partial solution that you want to still run search.
Got it. And that depends on the score that if you want to discard that path.
Yes. It can be based on a score. You can also have some threshold, so it never goes beyond a certain number of partial solutions, but it's mostly based on the score. So you can just keep at every time you can just keep sorting and make sure that you keep the top K scored thoughts, and then you just keep those in your frontier.
Got it. Another question is more technical problem. So I'm seeing an issue in my VS Code is when I'm trying to use the DeepSeek R1 abelian model, but it complains that it cannot find it. But even though I put Ollama list, I can see I already pulled the model before. I don't know if you have answer for this, but it's okay.
That's interesting. Can you share the screenshot later in the channel? I can look into it. I know it can be pretty sensitive about the naming, so if please, I think the best is if you share the screenshot of what you are entering and then what the error is. I may be able to figure out.
Okay, thank you. I'll paste the screenshot.
Sure. Yeah, but it's most likely just a naming or misspelling, because if you are seeing a model here, like the name here, and you use the exact same name, it should typically work. I mean, I haven't seen, in my case, I've never had issues. But yeah, please share, and then I'll look into it.
Okay, thank you.
Yeah. Peter?
Yes, thank you. You can hear me, right?
Yes.
Can you pull up that? Yeah, this page. So is it safe to say that Tree of Thought is an improved version of the one just to the left? Because you're going to get higher quality output with the branching.
Exactly. That's correct.
And so it comes down to if you can handle the complexity and if you want to pay for the extra inference, this would always be a better option. If you
So
can do.
that's a good point. It would always be a better option, assuming that you are spending the same compute as you are spending on the previous version.
Yeah. And can you comment on caching strategies? So in many business use cases, there would be similar invocations that could probably share a previously generated response. Do you have any thoughts? Do you have any thoughts on that?
Sure. I don't know if have you ever by any chance seen this page about caching?
I haven't looked at it, but I love it. I'll go read it.
Okay, this is going to be an amazing way just to get a sense of how caching works and what are the benefits that it can provide and how it's really implemented in practice. So it's a very like a detailed blog, and it also explains KV cache block and so on. So I suggest you take a look at this.
Thank you.
Yeah.
And one more question. Is there an easy way, if I want to search for all the models in Hugging Face that support tools natively, can I do that?
That's a good question. Yesterday, I think I spent like 20 minutes of my time on figuring out if there is an easy way for this. I couldn't come to a conclusion yet. I am planning to do more research on that, and then I can share with you. So what I like about Ollama is that it's easy. It just gives you, I don't know if it's like how up to date they keep this UI, but at least it give us some starting point on like, these are the thinking models, these are the tools model, and so on. In Hugging Face, I couldn't find an easy way. Again, I searched for some time yesterday, but I'll continue searching and figuring out what is the best way to basically the question is, how can we tell which models on Hugging Face or other backends are reasoning and which ones are not reasoning, right?
And natively support the tool with the standardized JSON output.
Yeah, I couldn't find anything. It's a very messy way right now. And there are these newer models like Kimi models and all those newer models. The only way, at least for me, is so I always go to their website and read the details and try to find if they are explicitly mentioning tool calling or not. The problem is that sometimes some companies or some labs, they release models and they do not also clarify if it's like fine-tuned for tool calling or not. So that makes this entire thing even more complex. I'll continue searching. If I find with something good, I will share with you. Prasad?
Hi, Lik. Thank you so much. Can you hear me?
Yes.
Thank you so much for such an informative session. I have a couple of questions. Maybe they are related, but it's more from the architect perspective I'm asking. I'm trying to do my best to be hands-on. My mind goes to the systemic thinking, so I hope you don't mind this question. So this is more what I perceived through this whole mechanism to scaffold your models, right? In a way, the tree of thoughts or all these are a way to scaffold your model, which is not very capable, like GPT-4 or something, but you are trying to scaffold all these instructions prompts so that the model yields better output. But then again, it adds complexity because you have to write all the tree of thoughts, for example, for a small model to make it better. So I want to ask you, when is it better to invest this kind of engineering time in building such complex orchestration around a small open source model versus paying for API calls for a more mature model like GPT 4.0 that may do the things right at the first time, and it's like a decision framework.
It's still context dependent, right? So my own opinion about this, again, there are different opinions, it's just personal opinion, but my own opinion always is that if we are a small startup, we should focus on building things as fast as possible. So it doesn't matter if we don't have the best search system out there to explore all different, like go over all the search space that we have, pick the best response. That's not the goal of the first iteration. The first iteration is always to build something that works and is as simple as possible. So basically the minimum like viable product kind of a thing. So, and then once we have that, then we evaluate and see how good it is and how much better we want it to be. And then we move from there. Sometimes it's just as simple as switching a model base LLM to a better LLM. Sometimes we may want to add complexity by adding like self-consistency. Sometimes we may want to do tree of thought. In practice, I think companies like OpenAI, they're not doing tree of thought because this is still a silly way of going and looking into the search space. In practice, it's Monte Carlo tree search and more advanced variants of it. So it all depends, and it's like, to me, it's like it must be a gradual process. You cannot start like if you have no chatbot or LLM as your product or service yet, you cannot start from building your best like Monte Carlo tree search system and then introduce this reasoning and thinking. To me, that's not the right strategy. To me, the right strategy is to start from here and see if it works. If it doesn't work, figure out why it doesn't work. Is it because the model is not good enough? Or do we really need to introduce chain of thought or not? Then we come to this step, and then here, and then here. This is just my own, philosophy of how to incrementally build something and incrementally improve it.
I agree, and thank you so much for that answer. I think a follow-up question on that is, like you mentioned, in a way, orchestration, right? Like, for example, can we build this kind of a smart router sort of a functionality where it decides based on, instead of a one size fits all approach, when to use which technique, like self-consistency versus tree of thought?
Yeah. So you can. And in general, routing mechanisms are very powerful. The next project has a routing component to it, so you would work on it this week. And it's not too complicated in general. Adding a routing mechanism is not too different from what we've seen in the first couple of projects. But it's a very powerful method in general. So you would practice it in project 5. Next week we would do a deep dive. And to answer your questions, yes, in general, you can, anywhere that you feel that an LLM can help you decide, you can just use an LLM and just call it a routing system or a router. Give it very detailed system instruction, what you expect it to do, and then it would do it.
Okay.
Just one more thing to add. In practice, I haven't seen to use a router to decide between different inference time techniques. I haven't seen that particular use case. It may work. It may even improve. I don't know. Just wanted to say I haven't seen it. But routing can be, in general, very powerful. You can just let an LLM to decide in certain cases what to do. And you would see it in the next project.
I see. Thank you so much. Last question, sorry, then I will hand it over. About performance. So like self-consistency and the tree of thought, they introduce, in my perspective, maybe if I use a powerful GPUs, then maybe less, but they introduce massive latency, right? Because we are making almost at least n number of sequential or parallel calls, because we have to kind of every time check, revise, right? The LLM is doing. So is it only suitable for asynchronous sort of batch jobs, or we can use it for real-time user-facing application?
Well, it depends on how, that's a good question. It depends on how you define it. I mean, if you go to ChatGPT, you select thinking. This is a thinking model. The instant is a non-thinking model. So when you type something, how to travel to moon, it would just start typing, right? So it's immediate. You can call it real time. Now, if you switch to thinking, you ask the same question. You can argue it's not real time because I'm just sitting here and it's just thinking. Now, OpenAI has a lot of good infrastructure. The thinking happens fast and they spend a lot of time on optimization. But still, it's been like 10 seconds, 5 seconds, 10 seconds now, and I'm not seeing any output. So is it still a real time? And when I tried the Pro, yesterday I used the Pro to ask a question, to ask a couple of questions, and each time it took around 15 minutes. And this time it took 24 seconds. So it is the nature of it. I mean, when you introduce thinking mechanism, so that simply means you are introducing more compute at inference time. So there is no choice but to wait for the computations to happen before you see the final response.
I see. Yeah. Thank you so much, Ali.
Yeah.
Thank you.
I mean, they are introducing some async process. I think like if you ask Pro something, and then you close your tab or laptop, and then I usually, when I ask something from Pro, I know it takes a while. I just go and do something else, and then I receive a notification on my phone that it's done. So it is definitely implemented in an async way to process the request and then just notify the user once it's over. And that's necessary because as these questions, as they introduce more compute at inference time, it takes longer. So there has to be a way to get back to the user. So yeah. Tanvir?
Hey, thank you, Ali. I have
Hey.
a general question. It's raw thoughts. I'll try to make an attempt to see if I can explain you. So far, at high level, my understanding is we have in this AI engineering journey, so far what I have seen is we have code level where machine learning and model related work, and there is tons of software engineering part where caching, memory, filtering, thinking, tool calling, there are a lot of software, good old software engineering problems. And then on top of those, you can build, it's kind of, I don't know if that's called applied AI, but you can build applications without getting to know the details of it. You can call models and you can build applications. So my question, I have few questions. So one is, what do you see in these big AI companies, the engineers are the same engineers who are dealing with machine learning model and all? They are the ones they are solving for software engineering part of it. I know a lot of time the answer is depends, but what do you see? And the second related question is, you are an AI engineer, like past 1 year or so, where do you spend your time? What kind of work in your role? I have third question, but I'll pause right now.
Okay, yeah, pause because I would forget anyway. So to answer your first, I think I already forget your first question.
The first question is,
yeah.
where do you see engineers?
Yeah.
Is the same engineer solving, working on model and machine learning and all those, and solving the software engineering? Because we see that it's a combination of both.
Yes, yes. So in practice, you are right. It also depends on the scale of the company. Bigger companies usually have these dedicated teams for certain parts of this entire engineering process. What I've seen that works in practice, at least in big companies, we have this. So there is this research side where people do research. Researchers, they don't care about if a proposed idea is practical, it can be deployed in product or not. That's not what they care about. All they care about is that how can they just advance this reasoning process or build a better search system. So that's one org or department, let's say. The other is like machine learning or AI engineers. Machine learning or AI engineers, they are the ones who typically take care of data collection, data cleaning. After data collection and data cleaning, take care of model architecture, model training, evaluation. That's it, evaluation. And these are mostly what machine learning engineers or AI engineers do. Now, there is another group, typically, which is focused on getting the trained model and trained and evaluated model, and then use it to deploy. And then that group is more focused on infrastructure, efficiency, making sure that they can deploy, monitor, observe the model, and all those kind of things. So these are the boundaries that I've seen in practice. Again, smaller companies may merge some of these different like engineering efforts, but in bigger companies, usually these are separate.
Got it. Thank you. And other question is, say, like we have different companies at different level. I mean, non-AI companies, we are trying to use these models and build some applications. So if we want to, I mean, after this course, I mean, in another 1 or 2 weeks, if we want to continue hands-on practice apart from your project, are there any active open projects would you recommend where we can go take a look at it, what's going on, if we want to also contribute, submit some PR and all for ongoing, I mean, hands-on practice until you get to a job where you are doing it day in, day out. So do you have any recommendations?
Okay, that's a very good question, and I don't want to answer it right now because it's a good question. I want to do a little bit more research, and also I want to also share my research in one of the channels because I think that can be probably relevant to many others. So if you don't mind, can you please post this question, and please make sure to post it in one of the channels, maybe general discussion. So first I don't forget, then I research, and then I would share my thoughts there.
Okay, yeah, I'll do that. And again, like I think you missed second question. If you don't mind, if you might share, which is like, what do you do? I'm just curious. What do you, in your role, where do you spend time?
I mean, my role over time, I was transitioned more, like I was an engineer, and then over time I got transitioned a little bit into a more like a leadership role, and that's not really. I really enjoy when I actually do code and do some engineering work. These days it's a little bit less and more on figuring out what is next and new initiatives and working with others to make sure things happening. But I would say over the last 2 years, probably I've been mostly focused on training larger scale image and video generation models. And yeah, I mean, some of the releases on Firefly, or some of those models are the models that I train at larger scale. So that was mostly what I was doing. And before that, I was mostly building search and recommendation systems at a scale. So a few years on search and recommendation systems, and then last 4 years or so, 3 or 4 years, it was mostly Gen AI and training image and video generation models.
Okay, thank you. And one last follow-up question, just to see, like, since, yeah, so the question is, I mean, there is software engineering leadership. As engineering manager, like you lead the team, software engineers and all. Do you see any difference in software engineering leaders versus like engineering manager, engineering leaders leading AI engineers? I mean, do you have any thought or any guidance, somebody, like, do you see any difference?
I don't know. I don't want to be biased, so that's why I cannot really share anything. I have seen examples, but I don't know if it would generalize what I've seen. But I can share you what I've seen. It's not related to Adobe or Google that I was working at. It is general, like what I've seen, like the trend or patterns that I've seen. What I've seen is that PMs and engineering managers that are not technical but are in the AI, they are generally more like I have to be careful of my wording. They generally, sometimes they overestimate what can be done with AI, and optimistic, which is good. I mean, whereas like leaders or like engineering managers more on the software side, they're typically more like, how to word it properly. They're not as like overestimating, the like AI capabilities, and they are more like they always consider using traditional software as well as the AI if it helps. Whereas people who are like non-technical people who are working on AI, they are always more like on the positive side of AI, and they're hoping that a lot of things can be achieved with AI. And sometimes I think they're good and bad in both. I think the probably somewhere in middle is the best place to be. Yeah.
Okay, thank you.
That was the best thing I could share.
Thank you.
Yeah. Sonia?
Yeah, so yeah, thank you. So like while you were here at this screen share, in this tree of thought, like you said, there is a width, yeah, say 2.
Yeah.
But say each of them is not producing 2 children, right? Then is it maximum 2, or what is it?
So yeah, I have to make some minor updates to the solution. You're right. In the generic one, we are using beam width to generate like 2 consequent like 2 thoughts. But in practice, width like theoretically means that the ratio of your expansions, which was the exact case that we implemented in the word ladder. We come up with like 4, I think it was 4, but yeah, we basically just come up with all possibilities to expand this node and then pick the top with like beam width ones. So is that?
So you mean like if we pick max 4 and pick the top one from it? Is that what we are doing? If 4 are possible, because in each depth 4 may not be possible, right?
It may not be possible, yeah. And which is fine. I mean, in this case, it's probably possible because from each state, we go over all the neighbors, and typically there are lots of neighbors. And then beam width is where here we just pick the top beam width ones. But if it's less than beam width, let's say there are just 3 candidates, it's still fine. 3 candidates would be added. So beam width is basically setting the max threshold. So for example, here in this example, let's say our width is 4. So that's why here we are adding these 4. We consider adding these 4 solutions. But here it's just 1. So what that means is that at this node, we were not able to expand more than 1.
Okay, so it means 0 to 4.
0 to 4, yes.
Right? Okay, thanks. And then if you could go back to your solution and towards the top, towards the top, please. All the way top. No, like starting. I remember in one of them, you added the question, draft, where we were doing the draft. You added the draft and the original question also.
Yeah.
So is that because, so the thing is that when I put the same thing in ChatGPT, it didn't give the solution it gave me didn't have the question in it. So is it? I mean,
You
is
mean
it?
you mean didn't have the draft?
No, it didn't have the original question in it.
So your question is why here in the draft we are also passing the original question?
Yeah. Like see at the second line you say role, user, content, question. So
Yeah.
is
It
it?
happens under the hood. I mean, when in ChatGPT you go and ask a question, it would format your question as the user prompt. And the best way to see this is tick tokenizer. I mean, this is the real GPT-4 example. So when you say you are a helpful assistant, what is your name? The model would see this. And what is this? This is the tokenized version of this. And what is this? This is the formatted way of, this is the formatted prompt, which is coming from these 2 components, user prompt and system prompt. And you can see the user is here.
So you mean that we each time we send it for a better draft, we should send the original question also, is it?
It depends on your design. I mean, in a simple chatbot conversation, it will always be part of the question, right? So here you say, what is your name? Then the model says something. My name is whatever. My name is ChatGPT. Then you ask, why ChatGPT? And then you are waiting for the model to answer. So now at this stage, the model would say this, everything, including the question, the original question. What is your name?
Okay.
This is basically a way to maintain the conversation and history. Now, this is a typical chatbot. In the examples that we had here, we had to also send question for the next draft. So because it just helps. If you see the lecture in sequential revision, in this stage, we are also sending the original question or prompt.
Original question
So
also.
we are just implementing this.
Prompt and response. Okay, got it. Yeah. All right. Yeah, that's all. Thank
Okay,
you.
awesome. Thanks.
Yeah.
So Mana?
Hi, Ali. Thank you so much for your time and effort on this. It definitely makes it so much more easier to understand. I have a very general question. So every time you say something released the day off or yesterday, I'm like, oh my gosh, whatever I learned is not useful anymore. So here's my question on that. So how do you keep up with all the latest AI news? And so do you have like any daily podcast you listen to, any website you check, like in particular that actually assembles all this, like does all this research for us? Like I'm just trying to look for some spoon feeding here.
Sure. Yeah, I'm happy to share. I think there was a thread. I mean, so please just post this question and tag me. There was a thread that I previously shared, a list of places. I mean, obviously, I cannot also keep up. I mean, this whole thing is evolving so fast. There are lots of things, and it's not easy. I do have a bunch of places and resources that I try to keep an eye on generally, and take a look. So that's one place. Some AI newsletters might be also good, the ones that collect news and share. I mean, one example is like, I think Superhuman, and then TLDR AI. I also curate the news there. So I have to also keep myself, up to date to provide those. But TLDR AI is another place where you can perhaps get some relevant, updates or news in the AI daily, or some other newsletters. But in general, it might be good to have one newsletter for AI news, and just keep an eye on other like blogs, or another place that I think I've shared before is Papers with Code. It basically has like daily and then weekly, monthly. So you can typically go to monthly, and the ones that they have super high votes or stars, they are good ones to take a look and see what they are talking about. So yeah, these are some of my like heuristics that I developed over the couple of years.
Perfect. That makes more sense. Yeah, definitely helps me. Thank you.
Yeah. Ravi?
Hey, Ali, can you hear me?
Yes.
Hey, thanks for your time and all the sessions. I have two probably quick questions. One is when I'm working through this assignment, right? At times, I see the output is chopped off, like sentence is incomplete and all that. And if I change the prompt and all that, I get a different output, obviously. But when such thing happens, like when the output is incomplete, the sentences is half and not even complete, why does that happen? Is it because it runs out of max tokens?
Yeah, it's a hyperparameter. You specify like maximum number of tokens that you want the model to generate. Here, for example, I specified max new tokens to 128. If I set it to 20, right after 20, it would be stopped, the generation loop, and then it would look like as if it's incomplete. So depending on what backend or what algorithm you use, there is always a parameter. You should always expect a parameter about number of new tokens that you want the model to generate. And you should set it to something reasonable.
Okay. All right.
And even in APIs, even in LLM APIs, they always have something like that. So you can always look for that and pick what makes the most sense for your use case.
All right. Okay, thanks. And my second question is that I was looking at the different models because I have an old machine. I can't run anything faster. It's all slow. So I noticed that there are some models like the DeepSeek R1 7 billion, which has the name has like Q4 underscore K underscore M. Like Quen some number and then Q4 KM. What does that mean?
That's a good question. I think
I can send you the exact name if you want. But it is a deep type of DeepSeek model.
Yeah, it also depends on who is hosting it. I mean, if they have their own notations, and I think generally it's not a big deal. I mean, there are just different ways to encode important information about the model in its ID or its name. For example, here in this example, right, 3 refers to the version of the Quen. Originally they had Quen and then they called it Quen 2, 2.5, and now 3. VL is saying that it understands images and videos. It's a vision language model. Whereas the pure LLM model does not have this VL. It's just Quen 3. This says the number of parameters. Now, sometimes they have like Q, which probably refers to quantized, but you have to just probably it's best to check the documentations. But most of the times for Q, or 4Q, it refers to it's quantized into a certain precision and things like that.
What is quantized?
So quantized means that in order to make the model more efficient, they are changing the parameters, like they are quantizing the so there are different, I can share some resources for quantization. But basically it's just an effort to make the model more efficient and by increasing or changing the precision of the parameters.
Okay, is more number for quantized, is it better or?
Generally, when it's quantized, the model is going to be faster.
Okay.
But it's going to be less accurate. Now there is an entire research direction where they try to quantize the model and still maintain the accuracy. So it's a trade-off.
All right. Okay. Thank you.
Yeah. Peter, go ahead.
Yes, hi. I'm wondering if you can comment on what do you think the valuable skill sets will be over the next 10 years for software engineers, given that this whole thing is changing so quickly and standards are still being established?
Yeah, I don't know. 10 years is difficult. I mean, I cannot even think about like 2 years from now or 3 years from now. This whole thing is moving so fast and a lot of automations is happening like across the board with AI. So it is difficult to say that. It also depends on from what perspective, like who is asking that question. Is it like as a startup or potential startup founder, or as a AI user, or as an AI builder? I think the answer would be different. But in general, I at least the pattern that I'm seeing, there is a lot of effort going on with bringing AI into robotics. And so, yeah, that is probably a pattern that I'm seeing more and more companies are investing into, using AI, bringing that into robots. And these robots could be for different reasons. It could be for personal use cases, for other use cases. So that could be another direction. But again, it's very, very difficult to tell what is going to be the next, direction or next best thing. Sorry, I don't think I can answer. I don't think I have a better answer than this. Yeah, but that's a good question. I think we should think about. 10 years, probably it's impossible. I don't think 10 years ago anybody would have correctly predicted today. But even 2 years, 3 years, I think it's a good question to think about. Yeah. Rahul?
Hey Ali, I don't know whether this is a little off the topic, but as we're building this agent, chat agent, what's the appropriate time to hand this over to a human agent? So we look at the responses, do we score them and see what's a confidence level, and then if it is low confidence, then we hand it over. Or if they just ask for a human agent, I don't think then everybody will start asking for a human agent if you don't do some basic validation. So in your experience, what could be the right trigger to handing it to a human agent?
So the question is, to what extent should we just use chatbots to answer questions or agents to answer questions, and at what point should we escalate it or bring it into a human?
Yeah.
Um,
And you can think about it if you want to answer it later. That's fine too. I can post it.
yeah, definitely. I cannot answer this on the spot, but I think the best way is, again, all these things, the way I think about all these things is to start from evaluation, right? So you should do a lot of study in general, like how your agent is doing at different levels. Like, is it always good in the first turn or the first two turns of the conversation? At what step in your data set or in your logs the agent starts to fail or the users start to complain? So I think it's just mostly about that, doing a very detailed, comprehensive monitoring and studying of how the agent is doing at each step in the conversation. And also, feedbacks from users, like at what point the users no longer find the outputs of the agents useful. So then that probably gives us some idea about, what is the right stage to just hand it over to a real person. But it's also very, very context dependent.
Okay. Okay, I think that's fair. That's fine.
Yeah.
Thank you.
Sandeep?
Hi, Ali. Thanks for the session. I think I have a simple question. So throughout the course, I think we have had a lot of hands-on sessions and everything, and there probably might come instances where we want to go back to the course content and go through, and you might get questions later on. I noticed that there's a new cohort opening up next as well, but would we have a chance to ask you questions after this cohort session if we run into some queries or we want to know something deep about a specific topic or anything of that sort?
Yeah, that's a great question. And I think one purpose of the platform and the course that we had was more on the community part of it. So basically, we all got connected, and then we formed this community, both on the portal and also on Discord. And then the access would remain on the portal for lifetime, and same for Discord. So I definitely encourage everyone, not only to ask questions, but also to helping each other, like answering questions, asking questions, sharing resources. And that includes me. I mean, as I see certain questions, like I think after the cohort ends, as moving forward, we are just a group of friends and community that we are just in some groups, and then we are there just to help and share with each other. So yeah, I think just if you have questions, or if there are questions that you can answer, I encourage you to write your question or answer the question. All right, so I think we covered all the questions. Thank you so much. And yeah, looking forward to next week. I hope you like the content for image and video generation. And then last week we would go over the project. Thank you, everyone. Bye.